Welcome back to this module on generation dispatch. In this segment, we'll be covering types of power plants. The objectives at the end of this segment, we'd like you to be able to draw a diagram for the different components within a power plant. We'd like you to be able to define the purpose of those components and then explain overall how each type of plant converts its primary fuel to electricity, and then describe the role of those power plants for system operations. That will be the main focus of this. A power plant has many thousands of components that all function under special conditions. Our goal here is to select those components and their overall system so that you can understand from an operator point of view how to interface with a power plant operator and the types of problems that that power plant operator may have to deal with under different operating conditions. And then towards the end, we'll cover the advantages and disadvantages for the different types of units. There is an extreme amount of controversy on what type of power plants are the best for this nation and around the world, whether it's nuclear, wind, gas fracking, or steam plants, coal plants, hydro plants. My goal is to give you the viewpoint from a system operator. I personally believe that we need to exploit all the different types of power plants. We need to make them work together. We need to make the load more adaptable, and not to make a judgment on what type of power plant is best for any part of the country. It's just natural, though, that the parts of the country that do have a high amount of wind are naturally going to wind turbines. Those parts of the country that have low wind are tending to invest in nuclear, and some are even continuing to invest in coal. But from an operator point of view, the general rule is that these plants are getting more complicated, and you as a system operator have to, the environmental constraints, the different types of conditions are making many more subsystems have to be added to those plants, and as a system operator you need to have an overall view of what is happening from the power plant operator point of view, because you are like in a command and control situation. You are tending to ask the operator to push those plants to limits under certain conditions, and it's really good for you to have an understanding of all the systems, all the way from the fuel intake to the outlets for both the gases as well as the products like recycled water, which can have a polluting effect. And so what we'll do, we'll go through each of the major power plants of different types in order. We'll start out with coal, which is the largest share of the U.S. electric fuel consumption for meeting electric demand. We'll then cover natural gas, which is growing very quickly due to the efficiency of new gas turbines as well as combined cycle units. Then we have the nuclear, which is roughly holding steady at 20%. And then we'll have hydro, which is holding steady in terms of the absolute value, but then declining somewhat in percentage. And then we have the wind, which is growing very, very quickly due to all the wind incentives. And then finally, we'll have the other renewables. So let's just take those in turn. We'll start out with fossil fuel steam turbines. Fossil fueled steam turbines can be fired by either fuel oil, natural gas, or coal. Coal plants are typically built close to coal mines, but we also have a situation where the coal can be shipped in by rail or by barges. Right now, there are very few plants run on oil due to the high cost of oil. After the Arab oil embargo, there was a definite trend to remove oil as a source for generating electricity. Obviously, it's still very much needed to drive vehicles and automobiles, but in the electric industry said, look, let's move to other types of fuel. Older plants can actually run on natural gas, but that is tending to be phased out because the newer combined cycle plants with efficiencies in the 50% range are much more efficient. So basically, predominantly, fossil-fired plants in North America are fired by coal. There's a tendency in North America to not be building coal plants due to the environmental restrictions and the heavy contribution to greenhouse gas and the relatively high percentage of CO2 compared to natural gas. But on a world basis, we see that the World Resource Institute is estimating and predicting there will be 1,200 coal plants with 1,400 gigawatts of electricity built across 59 countries, with approximately 3/4 of those plants being built in China and India. So basically, a coal-fired steam plant goes through a number of processes. We basically have the process where the coal is taken from the pile on a conveyor, and then it's pulverized into a very fine powder, and then that powder is mixed with hot air and ignited to cause an explosion and heat within the furnace, well, and a controlled explosion. And so what happens then is basically the carbon in the coal gets burnt and turns to CO2. So literally all of that carbon is being converted and taken up the stack. And then as it goes through what's called the precipitator, they take out the fly ash and they separate out the pollutants so that we have relatively clean air going up the stack. So that's basically the fuel cycle, taking the coal and burning it and turning it primarily into CO2. There's a separate cycle. Well, there's actually two other cycles. There's the water to steam cycle, and then there's another cooling cycle. So the water to steam cycle follows what's called a Rankine cycle. We take the pure water and we feed that through an economizer. It's called an economizer because the idea is to preheat that water and preheat it with some of the exhaust gas. So that's taking the heat in the exhaust gas, which would be wasted and actually doing some preheating of the water before it goes into the furnace. Then the water goes into the furnace water walls, these pipes, thousands of pipes going up the wall of the furnace, and then it gets heated. That's where the primary heating takes place. And it goes from low temperature, low pressure steam to high pressure and high temperature steam. And so the steam then has all that thermal energy in it, and then it goes through a small nozzle and it blasts against the turbine blades. So at that point, the energy in the steam gets converted into a kinetic energy of the rotating blades. After it comes out and it goes through several stages in the turbine, usually a low pressure, an intermediate, and a high pressure stage. And it actually goes through those stages in the order of it goes through the high pressure, then the intermediate pressure, and then the low pressure. So it comes out from that low pressure stage at a lower temperature and a lower pressure because it has dissipated its energy into the rotating energy of the turbine. Now at that point, it has to go through a condenser to return it back to water. And so at the condensing step, it is chilled by cooler water from an external source. And that cooler water can either be once-through cooling, where it comes from a lake or the ocean or a river. But more and more there's a trend right now, and especially in California, where they are banning once-through cooling. The problem with the once-through cooling is it's actually causing damage to wildlife, that it gets swept in to these intake grates. And so the big trend in California is to go to a closed cycle cooling. And the closed cycle cooling, you can always tell that, is that you will see the big, or we'll see it on the next slide, the big cooling towers, and the cooling happens through the process of evaporation. So basically, in summary, there's three cycles: the fuel to carbon dioxide cycle, the water to steam back to water cycle, and then the cooling cycle. There's an excellent animated 3D video of power plants published by First Energy, and you can find that on this site. But basically, through this 3D animation, they show you the coal being taken off through these huge scoops onto the conveyor. They show you the furnace, where the advantage of the 3D is they can do a cross-section and show you what's happening internally. They show you the three stages of the steam turbines. They show you the condenser. They show the effect of the latent heat of evaporization. Basically, the water that is helping with the condensing then goes through the cooling tower, and then the cooling tower decreases the temperature of that water even further. Basically, the efficiency in the power plants is a function of the temperature difference between the temperature of the water entering the boiler and the temperature of the steam exiting the boiler. So the more you can cool the water coming down as it goes in, and the more you can heat the steam as it comes out, the higher the efficiency. And then this is the characteristic of the closed wet cycle. Is you see these huge cooling towers, and you see the effect of the air is brought in at the bottom, and then it comes on up, and then through the latent heat of vaporization, typically about 1% of this water here evaporates, and that has a cooling effect in that the water coming into the tower is hotter than the water exiting the tower. And so that has a cooling effect in that the water exiting the tower is typically about 10 degrees less than the water entering the tower. Now, in power systems, as an operator, you need to be cognizant of the fact, are you dealing with a drum-type steam unit or a once-through? They have very different ramping characteristics and safety. The idea of a drum-type steam unit is that there's a drum which has the ability to store large amounts of heating energy, and the water comes on through, it turns to steam, and it cycles around this loop here pretty much at a constant speed. So we see that these units, which are typically older units, run at pressures below the critical point. The critical point of steam is a pressure where there's basically no distinction between whether it's water or steam. And so there's a distinct characteristic in how these systems are designed. So typically, we have a maximum of 2,400 pounds per square inch at 1 atmosphere of pressure. And like we say, the steam is generated in the boiler water walls. And we also have a superheating stage in the turbine where we make sure that it's really hot and all the moisture is removed. And the bottom line is there's little risk of mismatch in the heat going to the boiler based upon the amount of fuel. So we'll see in the once through that we have to be much more careful to make sure that the amount of heat that is taken away from this fluid is carefully matched to the amount of fuel that is being burned. So the drum basically acts as an energy buffer. And actually, when you're involved in the simulations and you're ramping these types of units, you get a certain increased amount of power out of that turbine for a few minutes based upon the amount of energy that is in that drum. And so these units tend to be very popular for what's called secondary units when you're doing a black start. You might have a black start unit, which is your hydro unit or a gas turbine, and then you'll build a cranking path to your drum type units because you know that those units have a good ability to ramp up from the zero load to the minimum and be under your own control. On the other hand, with the once through steam generator, we don't get that loop and we don't have the drum to retain that thermal energy as a buffer. So in this particular case, you're feeding the water in through a boiler feed pump into the economizer. Remember where it's being heated by the exhaust gases, and then it's coming through the water walls. And so at this point, if you have a mismatch, if you don't have this amount of water going through here at the right speed compared to the fuel you're burning, you can actually burn out those tubes. Those tubes can overheat, and then they can actually fracture. And so then you've got the unit literally has to be taken offline you have massive repairs. So you can see that effect. Literally, you'll have the boiler pipes, and there'll be a big fracture, like ½ an inch in that pipe. And so that means that you have to take that unit offline. Sometimes people will actually run them with small fractures in the pipes, and you get this huge, vicious whistling noise, and it's just really, really a scary type of thing to be around. So with these units, they inhibit the rate of response with the control mode, and the operator has to be very careful of keeping these two things in balance. And that's also why the operator does not like to keep those units below the minimum load point. You've clearly got to take the unit from 0 output and ramp it up to the minimum output. And as you're going from that 0 output to minimum output, the operator is balancing these things typically manually. Sometimes the instrumentation does not work very well at the lower temperatures and the lower fuel and water feed rates. And so there's a desire from the operator to get that system up to the minimum load as quickly as possible, and then have all the control systems take over. So like when you're doing a restoration, you have to you have to meet those guidelines of getting that unit up to the minimum load. And that can be a challenge, because in a restoration, you've got to find the right customers, and you've got to make sure you have the right transmission and distribution paths in place to bring that load on. So from a distribution point of view, you'll often have the transmission operator is in the middle of this. The transmission operator is saying they are basically driving the restoration plan, and on the one hand, they've got to take care of the power plant requirements, and on the other hand, they've got to get the customers. They'll be saying, give me load, please get some load on so I can bring those units up. So it definitely is a real balancing act. And it's really important then for you as the system operator to understand the different types of constraints of those different plants. These plants have very large steam admission valves, and there's one characteristic is that as that valve is opened, of course the megawatts for the steam turbines increase. But when you first crack that valve, we get what's called throttling losses. It's analogous to like when you first open a faucet in your home, you get that vibration and the noise. That is actually dissipating a lot of energy. So that's another part of the operating regime where the operator wants to stay away from. So there were some schemes called valve point loading schemes that would deliberately run the units faster through those operating regimes. More and more, though, there are local turbine control systems and computers that will take care of those issues. So in a lot of ways now, you as a system operator are one step removed from the actual mechanical and electrical controls, and that there's another power plant operator in the loop, and you have to be cognizant of the different operating modes of that power plant computer. There's a very big trend to replace governing systems, even on the older units, with more computer-based hydraulic governing systems. And so it's important for you to understand the types of operating modes and the characteristics of those control systems, and stay in sync with the power plant operators to make sure that they are in the correct mode. Now, in recent years, we've had a tremendous push driven by environmental concerns and enacted by the U.S. EPA to reduce all the different types of emissions from power plants. Nitrogen oxide can cause smog and acid rain, so they have been addressing that with low NOx burners, as well as a fixed bed catalyst that works in the actual flue ducts. And basically what the catalyst does, it takes the harmful nitrogen oxide and converts it to nitrogen and water, which are both very harmless substances. There's also been a requirement to extract the mercury. Even though there's a very low percentage of mercury in the coal, the fact that it goes up through the flue gas and then goes out into the environment, goes to the oceans, is eaten by fish, provides a hazard for human life. So we're seeing people have special scrubbers where they use what's called a silicon absorbent, and that attracts the mercury. It converts it to an inert, insoluble form, and you can collect that as part of the fly ash and embed it in concrete, and so it becomes very harmless to the environment. So we see these huge electrostatic precipitator systems which process the flue gas before it actually goes up the stack, and here's an example of the size of that, and you have ability to drive trucks underneath and take that waste product. So one of the other aspects is that we have the sulfur dioxide, and this can vary depending upon the coal type. But basically the way to get that out is they mix it with a limestone slurry and they convert it to calcium sulfate. But the process, as you mix it with the slurry, it becomes something that you can't dispose of directly, so they actually go through a very complicated chemical processing conversion where they clarify the water, it becomes a sludge, and it goes around the cycle to the point where we get clean water out of here, which is clean enough to put into a wetlands, and we get the dry cake, which we can make wallboard out of. So there are many systems that are being added now that, as a systems operator, it's good for you to have an idea, because any one of these systems could become critical. They could have problems. They could cause the unit to be derating. And if they go wrong, we can have very serious consequences to the environment, which is not what we want. And so here's an example of a Duke Marshall Station plant on Lake Norman, an actual lake in close to Charlotte, where I've had actually have been sailing on that. So the fact that we have products from these plants going into very delicate environmental situations is something that you as a system operator need to know about, and you need to be real sensitive to the power plant operator concerns. The power plant operator, from your point of view, you want the power plant operator to generate a certain number of megawatts over a certain period of time. But the power plant operator literally has hundreds of other variables that they have to be concerned about. All right. So one of the aspects, though, that you as an operator and the power plant manager are also concerned about is the overall efficiency. How many megawatt hours do you get for the coal that is being burned? And basically the efficiency has the characteristic that at low load it's a relatively low efficiency, and that's because we're taking all this air, excess air, and we're heating it and pushing it up the stack. But then as we pick up, the excess air is reduced. And so we have the fact that as the load picks up, and typically as we get close to the maximum output, we reach a peak where the unit is most efficient. So if we summarize, the advantages of coal plants is that there's a very well developed fuel distribution network with primarily rail and barge. We have a tremendous amount of fuel reserves. We see that the U.S. has 25% of the world total for fuel, literally enough to last for roughly 150 years. It's a very proven technology. The units run very reliably with a high capacity factor, and they're always available. Unlike wind, which varies based upon the wind speed, power plant units have a very high availability, and I'm down primarily for maintenance, or sometimes there may be outages due to equipment breaking. The disadvantages is that there's a requirement to add expensive air pollution control, and there's costly fines for non-compliance. So we're seeing projections right now with very massive retirements of the older units, because people cannot justify on those units that may be in the 200, 300, 400 megawatt range. It may be built 34 years ago, 30 to 40 years ago, going through these very expensive upgrades. And of course, with the enhanced concern about global warming and acid rain, and the potential cost of carbon credits, that is having a slowdown effect on building coal plants in North America. We can see that here, that basically for natural gas, the pounds of carbon dioxide for each million BTU is 117, whereas for coal it's closer to 200. So literally we have about a 1.8 times emission of carbon dioxide compared to natural gas. So there's it's very hard right now in North America for a new coal-fired unit to be justified compared to building combined cycle natural gas units. I also talked about the need to convert existing units from the once-through cooling to the cycle wet type cooling. And from an operating point of view, they have relatively slow ramp rates and do have some restricted operating ranges. And we're seeing, of course, the environmentalists are sitting on the coal piles with their wind turbine symbols, trying to make the case that we need to have a lot more wind generation versus the coal. And it's not quite that simple, but obviously from a investment point of view, there's enough uncertainty with coal-fired units. Even though we have tremendous coal reserves in the ground that could be used, we're not seeing many construction projects with a coal base in North America. But that over in a worldwide situation, there is a lot of development for coal plants. All right, the next type of plant we'll consider are combustion turbines. In a combustion turbine, basically we have an air intake and we compress that air on a compressor with the shaft, and a certain amount of energy, typically about 30%, just goes into that compression process, and then that air is mixed with fuel, possibly a natural gas, and that ignites to cause an explosion. So that compressed air then becomes air at very high temperature, very high pressure, and that impinges on the rotor blades to turn those blades. And then that generates the electricity. And then that air goes out through the exhaust. So gas turbines basically are two types, what we call industrial or utility turbines, which are heavier frames and blading, and we have aeroderivative types, which come from the aircraft engines. General Electric is a major supplier, and they have a number of models of different capacity, all called basically well known as frame 3, frame 5, frame 6, frame 7, frame 9. They have constantly improved in efficiency and reliability. They've constantly improved in terms of the longer periods of time between overhauls for maintenance. And the efficiency, like we said, through higher firing temperatures have become increased and increased. They're excellent for cold start and black start and load control. They can often go from cold start to full load in 10 to 15 minutes. One aspect, though, is they do need a roll down time. If one of these turbines was to trip offline, then there's a certain period of time when you actually have to let it roll down and even put it onto a turning gear. If you let that shaft sit without being turned, due to its heat, it will actually bend. It will sag in the middle, and so you then have a totally damaged turbine. So getting those turbines on that turning gear so that you don't get the bending effect is really important. You start them with a clutch. There can be issues with, so you can have either an electric motor or a diesel. If you want a black start gas turbine, then you really need to have a diesel there, because obviously if you have the electric motor and you have no power, you can't get it started. So it's important for you to know what is the actual type of a motor that's going to be used to start it. And then as that starting motor brings the turbine up to speed, there has to be a clutch to get it up to speed, and then that clutch can be removed. Those clutches can have mechanical issues. So for you to understand how those gas turbines are started is also an important part of knowing how to implement your black start plan. So here's an example of a GE frame 7, very heavy duty gas turbine with a simple cycle at 260 megawatts output. And it gets takes 11 minutes to get up to base load. That's excellent. And it can move at 40 megawatts a minute, and you can bring it down to 36% of the actual base load. So you've got a very good operating range to deal with. So what's happened is, with the efficiency in gas turbines and the price of natural gas coming down dramatically from like $13 to $3 per million MBTU, gas turbines have gone from something which you only ran under the most stringent peak conditions where there are no other options, and only ran them for a very small time of the year, to where you can literally run them economically close to base load conditions. So there's been a tremendous change in technology and the price. So as a system operator, you have to understand that full range of options. Some of the turbines may be very high maintenance, and so you hardly want to run them ever at all. Some of them, there's just not a problem. You can start them up, shut them down, and the maintenance costs are relatively low. The other major type of gas turbine are aeroderivatives. These can vary from 16 to 100 megawatts, and basically they're a derivative of the CF6-80C2 engine that was used on 747s, 767s, and Airbus planes. So GE has taken advantage of all the technology and expense that went into the R&D of those engines, and have adapted them to run for power plant and electricity producing applications. And they go by the name of the LM2500, LM5000, LM6000, and the LMS100. So one of the primary factors in the control of these turbines is the compressor discharge temperature. Right here, this is the hot air, which is the air which is being compressed, and in that compression process, air heats up, and then the low pressure turbine inlet temperature. And so these are limiting factors where the machine will seriously degrade if you go beyond those. And so we see actual control algorithms that are designed to run the turbine at maximum output by controlling and keeping those temperatures within limit. And we talked earlier about, you need to understand if the turbine is being run just in that mode by its local computer system, because it will not give you any governing response. If that is the primary goal of the control algorithm, which is to generate megawatts, which is to make money, then you also have to be cognizant of the types of control modes that these computers are actually following, and work with your plant operators to make sure that there's a balance between having enough turbines around that can give you the governing response versus just running them at the full output. G and the LM6000 is a major market provider and has by far the dominant market share of turbines in the 40 to 60 megawatt range. So we can summarize and say that the aeroderivatives, and here's a couple of examples, vary from 16 to 100 megawatts. The LMS 100 is actually the largest capacity of those units, and they can get to full load within 10 minutes, which is very good. As we will get into the balancing module, we'll find that there's a NERC criteria called disturbance control standard. After there's been a loss of a unit, you have 15 minutes to get the ACE back to where it was before you had the loss of that unit. And so these types of gas turbines are an excellent solution, where you can actually start them up from cold and get them online within that 15-minute period. And we see very good efficiencies, 42% for the LM6000, 44% for the aeroderivative, and that's not even accounting from what we'll call combined cycle, which raises it even further. And so then the large utility ones can have even a greater output. And again, they can't quite get the full load in 10 minutes, but they can get very close to 160 megawatts. And so they have excellent ramping and control capabilities. So in summary, there's been dramatic improvements in the design of gas turbines in the last few years. And the manufacturers literally are looking very closely at the NERC standards and making sure that they design those turbines to provide full advantage for both ramping and disturbance control and restoration. So in summary, we can get to full capacity in a few minutes. They have great black start capability. They have very fast installation times. And you can introduce them in small increments. You don't get the sulfur dioxide emissions, and they're primarily regulated on the NOx emissions. Here's an example of fast delivery. In the Iraqi power system, they were at about 5,000 megawatts after the toppling of Saddam Hussein, and over a period of time, the actual this here is the actual forecast base of load, and this is the actual demand, and they have not been meeting the demand. The actual supply is less than the native demand, so they've been literally going through rotating blackouts. But GE has supplied the Iraqis with 56 gas turbines that have been in service, and they're now planning to add 7,000 megawatts and an additional 56 gas turbines to bring the demand up to be much closer to the, to bring the supply up to be much closer to the demand. And there's been a total of 130 installed to date. So literally, predominantly, the rapid increase in the supply of electricity in Iraq is being supplied by gas turbines, and in the future it will move to be supplied by combined cycle units. So that's just one example where through standardization of the packaging you can add an enormous amount of capacity in a very short period of time. So summarizing again, the early disadvantages of gas turbines have largely been mitigated. We no longer have the situation where they're very inefficient at lower load. They're no longer so expensive to run, especially with the lower cost of natural gas. And more are actually designed to run under base load conditions. And this shows you an example of the LM6000, where there is every 4,000 hours we need an outage for inspection. The hot section can be replaced within 3 days. So if it was running if it was running continuous, this could be 3 years. Every 50,000 hours, it needs to be sent back to the depot for refurbishment, but GE can actually lease you an interim one to take care of that period of time. So there's been a tremendous improvement in the overall maintenance plans. All right, now let's move on to combined cycle systems. The combined cycle system basically has a hybrid of gas turbines and steam turbines. So we take the hot exhaust gas that's coming out of the combustion turbine and feed it into a heat recovery steam generator. Rather than just letting that gas go up and heat the environment, let's take advantage of it and feed a separate steam generator. We're getting efficiencies between 50 to 60%, tremendous increase. And we can have different combinations. We can either have one combustion turbine matched up to one steam turbine, but often you might see 2 or 3 combustion turbines driving one steam turbine. So here are all the different systems. Basically, we take the air, we mix it with the natural gas, we fire it, we feed it through the gas turbine. We take the exhaust coming out through this heat recovery steam generator and then take that hot steam and feed it through a steam turbine. Then we have our cooling. We have to take it comes in as hot steam, it comes out as as lower pressure, lower temperature steam. We then have to take that through a condenser, turn it to water, and then we have another cooling tower. And so we basically have the two cycles of the natural gas being turned to a hot gas, and then we have your steam cycle of the water going to steam and then back to water. And the net result is we actually have two generators. We have the generator being driven by the gas turbine and the generator driven by the steam turbine. And you, of course, as a system operator, have to realize the dependencies. You can't have the steam turbine running unless you have the gas turbine running at a certain level. Again, there's a very good animation of the Metcalfe combined cycle unit available on YouTube. And this is a nice three-dimensional simulation, and it shows you the cutaways. So here we have the gas turbine putting out the hot gas. We see the actual internal layout of all the steam exchanger pipes, where the hot gas is being blown across these boiler tubes. And so the water coming through here is going from a cold state to hot steam coming out to drive the steam turbine. And we see the condenser taking place, and then the cooling is, in this case, is actually taking place with fans, and they take that water and they blast it down like a spray, so we get the latent heat of vaporization having an additional cooling effect. So two characteristics of a combined cycle plant is you see the building, which is the heat recovery system, typically going up at a sort of an angular shape, and then you see all of these condensing systems on these buildings along here. And I highly recommend that you spend some time and go through that. So what happens as we go from single cycle to combined cycle, we get this efficiency improvement from around 40%, depending upon the type of turbine, in this case, from around 40% to above 50%. So we're seeing a very wide deployment of those systems. And again, in the Iraqi power system, the initial deployment will have lots of combustion turbines, but in order to get from to the point where they get up to close to 35,000 megawatts of load, they will be deploying very standardized combined cycle units, because in their case they do have tremendous natural gas resources. They're investing in new oil fields, and they're putting in all the infrastructure to have natural gas-fired steam and combined cycle systems. So again, we have high thermal efficiency, relatively low initial cost, high reliability, low air emissions, low carbon dioxide production compared to coal, short delivery time, and they can be a very good complement to wind. Basically, as the wind comes and goes, the combined cycle units have the ability to fill in. And with the fast start ability and the ramping ability, effectively what it means is that all that wind energy is further reducing the net effect and reducing the total cost and the amount of fuel that you have to burn. So that's one aspect that you will tend to see those types of systems working together more closely in the future. But again, from a system operator point of view, you have to be very cognizant of how those units can ramp, what their minimum load abilities are, and use that as just another very powerful tool in your overall range of dispatch options. Right. The next topic we will cover are nuclear power plants. Basically, the U.S. has had 103 operating nuclear power plants. Since 3 Mile Island, basically there have been no further plants built in the U.S., but they do produce close to 20% of nuclear generation. And there are two types: pressurized water reactors and boiling water reactors. And basically they use the fact that when we have two atoms of uranium splitting, there is a fission process, which means division, and energy is given off from that process. The characteristic of nuclear power plants are the reactor shielding vessel, and you see a case here where we've got 4 reactor vessels, and these are very highly reinforced concrete designed to withstand aircraft crashes to protect the reactor from emitting into the environment if there should be an accident. So the pressurized water reactor is actually quite similar from a steam point of view to a coal-fired system, except we're replacing the actual furnace with a nuclear reactor. So we take, these typically run supercritical with pressures above 2,000 psi and temperatures above 500 degrees Fahrenheit. And the core of the reactor are these fuel rods, basically 12-foot long rods with uranium fuel pellets. And those pellets are going through a fission process, and they are emitting neutrons. And the control rods absorb those neutrons. So basically the rods are lowered into the reactor, and that will slow down and stop the reaction. As you pull those rods out, then we reduce that absorbing effect, and the reactor goes critical, and those neutrons are flying apart, and there's a chain reaction, which is creating the heat. So to remove the heat, we have to cycle water through the rods and take away that heat, and then feed it into a heat exchanger, which then will take the water, convert it to steam, and then we drive the turbine. So that's the secondary loop. From the heat exchanger, we take the water, we produce high pressure and temperature steam that drives the turbine, which goes to low pressure and temperature steam, which we then condense and back to water and around the cycle again. Right, now the boiling water reactor, it's similar to the pressurized water, but there's no intermediate steam generator. In this case, the actual fluid that is going through the reactor is the same steam fluid that is going through the turbine generator. The moisture has to be separated, of course, because you've got to have pure steam going into the turbines, otherwise water will cause damage to the blades. And so that the dry steam drives the turbine, and then the water is sent back to the core. Most of the reactors being built today are the pressurized water reactors, but there's quite a few boiling water reactors that are in service. Now, the uranium process goes through a number of steps. It's important to understand, if we're looking at the market price for uranium, is it processed and purified, or is it the basic yellow cake? So it is mined, and then it's converted to UF6, and then it goes through an enrichment process. That enrichment is often dealt with centrifuges, which separate out the higher density uranium. What you're trying to get is the U-235 is the uranium that is fissionable. And this is where a lot of the controversy is in Iran, is that they have tremendous uranium processing plants that are spinning these centrifuges, and they're trying to separate out and create the enriched uranium. And as you might have heard about the Stuxnet bug actually took control of those centrifuges and made them spin at extra high speeds and caused a tremendous amount of damage. So the fact that that's a whole separate story about computer infrastructure protection, that we're now starting to see that the fact that the processing computers can be bugged and used for devious means. So that is a situation that we'll also be getting into under our CLP classes, is that the infrastructure of the computers controlling everything has to be taken care of from a security point of view. But through that processing then of enrichment, we get U-235, which makes up 3 to 5% of the net uranium, and that is what is used in the fuel rods. And then after the reactor has been used to, where that fuel becomes depleted, it goes into storage and reprocessing, and then it can go through long-term storage and disposal. So the advantages of nuclear systems is that the fuel is relatively inexpensive, significantly less than the fuel price. If you look at a million BTUs per dollar, it's less than any other type of fuel except hydro and wind. It's not too difficult to transport the fuel. We don't have any greenhouse or acid rain effects, so there's like zero impact on carbon dioxide in the environment, and they can be very ideal baseload units. Of course, there are some disadvantages. There are very high capital costs, very long construction cycles. In America, the government literally provides financial guarantees for those utilities that are building these systems. And we have the long-term waste storage and the fear of the nuclear fuel being used for proliferation and creating weapons. We have the not invented in my backyard syndrome, and it's a political issue. And when you lose a nuclear unit, it's a major contingency. And as we see, I guess one of my colleagues actually worked in this environment. Maybe you could tell us a story, Calvin. This looks like an eerie place to be working. Is it? I mean, is it that? What's it feel like?
That's exactly me. That would be right me in the middle there, doing that. It's big, deep, cool, and these small little squares. You must trying to move things around very slowly. And it glows blue like that. It's real pretty, actually.
It's really pretty. Wow. So this shows, the pool for storing the fuel after it has been spent, and there has to be cycling of clean water through that to keep the temperature reduced, because the spent fuel is still going through a much lower level fissioning process and giving off heat. And then, of course, if we move the fuel from the on-site storage, there are these huge nuclear fuel containers. But what's happened right now, due to the problems in getting a long-term fuel site allocated, there was a lot of push to get something built in Yucca Mountain, but naturally the people in Nevada did not want that to happen. So in the most cases, the fuel is being continued to be kept on site at these plants. Again, I recommend some nuclear plant videos. The United Arab Emirates is looking to, their whole economy is based upon low cost of energy, and so they are looking to build some nuclear plants and have some excellent videos online. All right, the next type of plant we'll consider are hydro plants. Having growing up in New Zealand and then moving to the Northwest, this is one of my favorite types of plant to tour around. And so when we're on vacation, my wife is very tolerant. I love to go around and just look at all the moving parts, and touring power plants is a tremendous hobby of mine. So let's go through this, and we'll go through some of my personal favorites. So hydropower basically converts the potential energy of water to electrical energy. And we have to deal with the reservoirs, the penstocks, the turbines, and the powerhouse. Here we've listed some of the major plants in North America, well, in the United States, with Grand Coulee being the largest at 6,800 megawatts. Chief Joseph Dam also on the Columbia system, John Day Dam on the Columbia system, and the Dalles Dam. And then we have the Hoover Dam in Las Vegas, and then the Robert Moses at Niagara Power Plant, and we have Bath County. So in the Northwest, we have tremendous resources. If we total up the megawatts that are available on the main Columbia, the Snake River, the Pend Oreille, and Kootenai in BC, we are up to 35,000 megawatts. So our objective is for you to be able to describe the major components of a power plant, understand the equation for power generated based upon water flow and head, describe different types of turbines, and describe the Northwest hydro system. This has a huge impact right throughout the western United States with reserve sharing agreements. And then we'll describe elements of the Wanapin Power Station on the Columbia, as well as one of my favorites from New Zealand is Manapuri. So the elements in a hydro station are shown here. Basically, we start out with a reservoir and an intake, and then we have the penstocks coming on down to the power plant chamber. Very often these power plant chambers are buried in the earth, and you have to go through elevators or drive down long tunnels to get access to them. And then through the turbine, we have the discharge into the tail race. There may be a surge chamber. The surge chamber is to take care of pressures. If the valves are closed quickly or open quickly, the idea is that this relieves the pressure. In this particular case, this is something rather unusual. The surge chamber is actually on the downstream side of the reservoir. And that's basically because this system can also act as a pump storage plant. So in a pump storage mode, the turbine is reversed and is actually pumping the water from the discharge area back up to the reservoir so it can be used the next day. And so I believe in this particular case, the surge chamber would take care of the fact that if there's a sudden loss of power to the motors, then you've got all this water rushing on in. Instead of it slamming up against the gates here, the pressure will be relieved by the surge chamber. So you can see surge chambers either on the downstream or on the upstream side to take care of those pressure transients. The basic equation for the generation of power in megawatts or in watts is that it is the efficiency of the turbine by the density of the water and the acceleration of gravity. These two variables we can't really change, but what we can change is the head. So as an operator, you have to be aware of the fact that depending upon the height of your elevator, you may have a greater capacity. As a system operator, you have to be aware of the fact as a result of the variation in the height of the reservoir, you may have a different head. That will, as the head increases, you can get more power out of the turbine. And then, of course, the main variable is the flow rate. As you open the wicket gates, you get more flow through the turbine, and that's the primarily factor that governs the electrical output. Individual plants may have local computers that are actually dispatching all the individual power plants, or hydro units. A hydro plant may have anywhere between 2 to 4 to 10, is quite common, but as many as 20 units all running with their own penstocks and their own turbines. And there's often a local power plant computer which is figuring out the actual dispatch of the total requirement that you as a system operator asked for and making sure that those turbines are all running at the most efficient point. And the efficiency itself can be a variation of the power that it is generating. There are three main types of turbines in common use. They basically work for different heads. So the Kaplan works well for the lower head systems from 2 to 40 meters. And the basic principle is the water's coming in through these wicket gates and then providing a pressure on the turbine blades, causing the blade to rotate. On the Francis turbine, it's designed more like the water comes from the outside and pushes on the blade and goes out through the middle. And then the Pelton is more an impulse type where it's designed for very high heads and the water is impinging on the blades and causing them to rotate. There's a very good animation on the YouTube that shows the dynamics and the cutaway sections for a hydro plant that I encourage you to watch. Often the penstocks are actually buried inside the concrete for the actual dam as shown here. And so the water comes on down through the penstocks and into the turbine, rotates the rotor, and we produce the electricity. And this is clearly a Kaplan type turbine, just looking at its shape. So an example of a low head turbine is the Wanapum Dam, located on the Columbia River with 10 turbines all running in parallel. This shows you that in this case we don't have separate penstocks. We have the river, which is dammed with a dam which is just over a mile in length, and then we have the water pushing into what's called the scroll case, and we have the wicket gates, which as those gates open, the water is allowed to pass through and it turns the rotor. From a system operator point of view, one of the things you have to be aware of is what's needed to operate this unit as a black start unit. And basically everything internally can be started except for the thrust bearing. Basically there is a bearing at this location right here. Under black start conditions, the turbine is at standstill, and so the issue is how to get that turbine rotating. The main thing you have to do is provide high pressure oil to the thrust bearing. So you need to have either local power from a diesel or from batteries to get that high pressure oil going into the thrust bearing, which lifts that thrust bearing just a fraction of amount, and then you can start opening the wicket gates to get the turbine running. If you did not have the oil pressure running here, then you would heavily score and damage that thrust bearing. And in taking a tour of this power plant, the plant operator, Bob Jordan, said that if there was a really desperate situation and say there was leakage coming into the plant due to an earthquake and there was no backup diesel available, he would actually start the turbine and suffer the damage of that thrust bearing, because that action could save the power plant. So that's an example where under extreme conditions it's okay to break some of the rules, realizing that you'll suffer a little bit of damage versus losing an entire power plant. So I thought that was a fairly innovative example of thinking through the different contingencies. Yes, that's your job as a system operator or a power plant operator, is keep thinking through all the possible things that can happen and how can you come up with a survival strategy under the very worst conditions. So this is an actual shot of one of the used turbines as they went through and refurbished all the units and upgraded them. And this is clearly shows the type of rotors and blades we have on those types of turbines. One of the things that you have to watch for is what's called cavitation. At a certain speed, the water coming through here can actually turn into air bubbles. And the process of those air bubbles being formed and collapsing causes cavitation. If you looked at these turbines during the maintenance, you'd actually see like a 1/8 inch channel where it had been eroded away from the process of cavitation. And so the power plant operators clearly want to stay away from those particular power outputs that cause the cavitating effect. I was actually down right next to the scroll case when Bob took that into a cavitation zone, and the vibration and the noise was really huge. And the other aspect you have to worry about is we have to allow the salmon to come on through here, and clearly the cavitation can cause damage to the fish. And I have to believe that it really we must scramble their memory imprint. The salmon basically have an imprint of all the smells they go through as they go through the spawning grounds out to the ocean. So I can only imagine the effect that has on the salmon brain as you have those huge vibrations as they're going through those turbines. And Grant County has actually made some special arrangements to take care of bypassing the salmon through those special chutes that we'll get to later. So one of my favorite power plants, which I still have not had a chance to visit, is Manapuri Power Station, and it's part of a very famous movie. This is Doubtful Sound, which was where all the filming was done for Lord of the Rings, when they were in the scenes where they were going through on the boats through the very clear water and through the mountain scenery. And so you can actually tour there. And there's a model of how the Manapuri Dam is set up. So there's an elevator which you can take from the switchyard on down, and here's the penstocks, and then the outlet is through a large tunnel to this sound. When they designed this, they did not anticipate the level of back pressure from the tail race, and it was designed for 700 megawatts. But if the operator actually ran the unit at full output, the water would actually back up and flood the control room. So that's another case where, as an operator, you have to be very conscious of the limits of your system. Otherwise, some very dangerous things can happen. They actually went through an upgrade. This is a turbine hull. This is Francis turbines by looking at the wheels. And this, again, is buried deep down in the ground. So if we look at the different types of constraints, especially in the Northwest, fisheries and preservation of the salmon has become one of the dominant objectives to make sure that the fish can both migrate down as well as upstream. But we covered cavitation zones, we can have irrigation constraints, we can have municipal and industrial water supplies where you've got to have the level of the rivers and the lakes at a certain height. We can have navigation issues. It's very common for power plant operators to be called by houseboaters that happen to be stranded on the lake, wanting people to raise the lake so they can get off and get back home. But that clearly can be a lower priority. Just the beauty of parks and the fact that if the water is released too quickly, it can cause eroding effects is a major issue. And at certain times, you may have to flush the sediments from the reservoirs, and so you may actually spill water to kind of get that increased flow. And then flood control obviously is a huge part of this, is making sure that the downstream flows are not so great that you can mitigate the effect of flows. So here's an example of a fish bypass, which has been highly recommended and cited by environmentalists, is implemented by Grant County PUD, and it provides a very high survival rate for the different types of salmon as they are encouraged to take that bypass versus going through the actual turbines. So hydro plants can be used in two types of modes. Basically, we'll get to this in the dispatch section, but during the springtime when there is an excess of water, you really want to use every possible cubic foot of water flowing down. Otherwise, you're spilling it, and so you're literally wasting it. So under springtime conditions, you may be running that power plant like a base load unit, flat out the whole time. In the summer, when you don't have so much runoff, you may not be able to run the plant at full capacity. Let's say you can only run it at 40%. Then at that point, you tend to use it in what we call a peaking mode. You're tending to run that plant during the peak conditions because that's when the cost of energy is highest, and that's when you have the biggest impact with that finite hydro resource. They can be ideal black start units because basically all you've got to do is get the power to the thrust bearing, and then you have tremendous amount of power from zero to full load that it can pick up. You don't get the same minimum loading problems that you have with coal-fired units. You just basically have the cavitation zones to stay away from. But you can run power plants, hydro plants at very low outputs quite safely. When you look at a power plant, you may come up with, well, why not just put all those 10 units and run them in parallel? And then you have tremendous amount of black start cranking power. But it's not as easy as that. Basically, when those plants are not synchronized to a strong system, they actually have an issue with the governors running right at 60 hertz. So if you try and start a number of power plants all up in parallel without being attached to the system, they literally will oscillate against each other, and the dynamics of those governors and those huge wicket gates can be a very unstable and frightening situation. So in many cases, what we find is that we basically have to start one power plant up and one hydro unit up, get it tied to the system, and then you can start bringing the other units on. So the advantages then, it's a long-term, low-cost source of energy for many years. Water is a very clean, renewable source. Everything is produced in the USA, and it's generally available as needed. And it can provide irrigation, can provide food, and can totally change the living conditions for an entire area. And as I mentioned before, the Northwest has been particularly blessed with tremendous hydro resources across the major river systems. This shows just the extent. The dark blue are the hydro plants. We see the green are biomass. So there's a surprising number of biomass plants, but these are mainly smaller units in the range of 10 to maybe 100 megawatts on the upside. And we see more and more gas plants being introduced and a very small number of coal-fired plants. And one nuclear plant at Columbia. If we look at the disadvantages, there are very few once they're built. Clearly, during the initial development, there is the requirement for mass relocations of people over large areas. So we are pretty much in a mode where hydro plant development in the U.S. is just done on a very small scale, where there's not a large impact. We have had the effect on the migration of fish, which is now a very dominant concern in how all the Northwest plants are operated, and it can cause lower oxygen levels in the water, impacting wildlife. We have the issue to deal with seasonal variation, and then of course this graph here shows you the effect of basically drought-type conditions. This is the percent of U.S. electricity that is being met by hydro, so it's coming on down as the amount of hydro installed is pretty flat, and we're adding more and more generation. And then this one shows the thousands of megawatt hours that are produced. And we see a large variation from the drought years to the years where we have an excess of rainfall and snowpack. And so that's an uncertainty that really happens year by year that has to be accounted for with the overall energy planning. The next segment of this module will cover wind turbines. The objective is at the conclusion of this segment, we'd like you to be able to describe the components of a wind turbine, describe the equation for wind generation as a function of wind speed and area, and then describe the role of wind turbines in system operation. So the components of a wind turbine, this represents a 1.5 megawatt turbine, and more recently we're up to around 2.5 megawatts with even longer blades and swept areas. But the components basically include the tower, then the rotor hub, and then the blades. 3-blade turbines are the most popular design. They have the smoothest operation compared to 2 blades. So the equation for generation of wind is that we take the kinetic energy of the air, which is 1/2 the mass times the velocity squared, and from that energy, based upon the energy that is passing by the blades, we develop the power equation. The rate of that energy passing the blades is a function of the speed of that mass of air. So the faster the wind, the more mass that is passing the blades, as well as the more energy that is in that mass. And so the net result is the power out of the turbine is 1/2 the Betz coefficient times the swept area times the density of air times the velocity cubed. And the velocity cubed impact clearly provides the incentive to have turbines in areas with the high wind speeds. The Betz coefficient of performance is based upon the fact that as the kinetic energy of the wind is transferred to the blades, if we were to get 100% of that energy transferred, then the wind would be coming to a standstill when it actually passed through the blades. And that clearly is not going to work. So the Betz law says you can only convert around 59% of that kinetic energy into mechanical energy. And modern wind turbines have a Betz coefficient that is around about 35%. We're seeing tremendous growth in the actual physical size and capacity of wind turbines over time, as new technology has been introduced and new materials have been used to make longer, stronger, more powerful blades. And so this shows a trend with wind turbines being projected, and very commonly right now we have wind turbines in the 2 to 3 megawatt range, and developments are taking place to get that up to 5 megawatts. And there are developments also occurring to make sure that we can get very large swept areas so that these turbines will work economically even in the lower wind speed regions. So here's an example of the power output curve of a Vestas V90 turbine. We see the characteristic that there's actually a cut-in speed. There's a certain low wind speed where the turbine, the blades just don't rotate at all. But they're being designed to operate with lower and lower cut-in speeds. So here's the speed at cutting in and providing a small amount of power at 5 meters a second. And then, of course, we have the flattening out, where as the wind speed gets up below 15 meters a second, the turbine output has to flatten out because the rating of the generator will not handle continuing to go on up as the cube. And then we get up to a actual cut-out speed, typically in the range of 30 to 35 miles an hour, where the turbine is actually taken offline. So the main issue when we look at the roll-in system design is that the wind is not blowing constantly at all times. It's varying, so we typically get a load factor in the range of 25 to 30%. And therefore, these turbines do require additional reserves to account for their variation. And the basic philosophy in operation is, if it's running, you use it. So from an operator, from a decision-making point of view, you don't have a lot to decide about what the output of the wind turbine will be. Your goal is to have a good prediction of the weather and the wind, and then run the rest of the system to balance the actual changes that you have to deal with because of the output of that wind turbine varying. So the advantages are that they can be built very quickly. Literally, people are installing entire farms with capacity of 1,000 megawatts in a matter of half a year. And the wind is a very clean fuel source, and it is very abundant. And the operating costs are very inexpensive after the initial installation. The disadvantages are the wind is intermittent. If we look at a graph which shows for given days of a month, we see such a tremendous variation of wind from one day to another. Now, it's not as bad as it may seem looking at that graph. On a given day, you can actually get very good forecasts based upon a 95% confidence level of where your wind will be and where your output would be. So day to day, you actually have a better, it's not like on a given day you show up at 6 in the morning and you're not sure will you be running with this curve here or with this curve here. They've made major advances in wind forecasting programs to give you an actual confidence bandwidth that you can expect with the wind to be within. In many cases, of course, the people like to live in the coastal areas where the climate is nice, and the wind comes more in the mountainous and plainer areas where the climate is not so good. And so most people do not want to be living somewhere where the wind is blowing at 30 miles an hour every day. So we have a catch-22, and so basically the wind is requiring longer distance transmission lines to be built, and we're seeing some very innovative schemes in Texas where the wind here is in the northern panhandle, and they have what's called CREZ, competitive renewable energy zones, where they're encouraging private enterprise to build the transmission lines to bring that energy into the major load centers in the Houston and Dallas areas. So they do require complementary reserves, and as we mentioned earlier, combined cycle plants are an ideal complement. That the combined cycle units, on the days when the wind is dropping off, you're running your combined cycle units to fill in that particular valley. And so the net result of the wind then is to drive the effective cost of that gas down even further, because you're complementing the burning of the fuel with all the times when you're getting the wind essentially free from your turbines. So if we review the overall objectives for this entire module, covering the various types of power plants, all the way from coal-fired steam units to combustion turbines, to combined cycle, to nuclear plants, to hydro plants and wind plants. At this point, you should be able to draw a diagram of the different components for each of those types of power plants. You should be able to describe the purpose of those components and then describe how each plant, whether it's a nuclear unit, a coal unit, a hydro unit, a wind unit, turns its primary source of fuel or energy to electricity. You should be able to describe the role of those plants in system operations and list the advantages and disadvantages of those different types. Thank you.